This is the presentation of the 10th place solution of the latest COVID-19 detection competition on Kaggle using X-rays. My name is Guanshuo Xu. Currently, I'm a data scientist at H2O.ai. So we have around, in this competition, we have around 6,000 X-ray studies, and most studies have only one image, and some studies have more than one image. Totally, we have 6 targets to predict. There are 2 image level targets. The opacity, which is the only bounding box target, and the non-target, which means there's the probability of no opacity. So there are also 4 study level targets: negative, typical, indeterminate, and atypical. So during training, we can assign study level labels to images, and during testing, we can merge image predictions into study level by averaging. So basically, we don't during training, we don't give special treatment to study level targets. We simply treat them same as the image level. So we have 6 image level targets here. So for the first model, I tried to use a single model to predict all the 6 targets, since we have bounding box target, which is the opacity. It is natural to use object detection model. Here I used efficient DAT model, and so now the job is to transform the 4 study level targets, which originally they're just single class digit, and we need to transform it into bounding box to serve as input for our detection models. So previous experience tells me that I can use the whole image, which is the biggest bounding box of an image, to serve as target for the study level. And since the 4 study level targets are mutually exclusive, so that means there will be only one bounding box of the whole image to represent one study level target for each image. So because of the special treatment of the label assignment of object detection, if the 4 study level targets are not mutually exclusive, there could be some conflict, so it won't work. Here, because they are mutually exclusive, it will work. So there's still one target left, which is the non-target. Because of this mutual exclusive reason, we can't do the same for the non-target, which means using the whole image as bounding box. So we have to left non-target as blank during training, and to predict it, we can simply, because none means the probability of no opacity, we can simply use the probability of the top opacity bounding box probabilities to predict it. Here we show the equation here, and above there's a table which is an example of label of input image for our object detection model. So by the way, this model alone can rank 27th on the private leaderboard. To improve it, I trained some expert models to enhance the performance for each target. So there are some efficient nets for study level targets, and efficient nets for non-target, and YOLO models, which is also another type of popular object detection model, for the opacity bounding box prediction. So all the expert model predictions and the original efficient net model prediction will be assembled or blended to generate the final solution. So on the left side, you can see that we have YOLO model that will generate opacity, and we have efficient net, which can generate opacity and also study level labels. We have efficient net to generate study level labels. We have efficient nets to generate non-labels. And for the opacity bounding box, we use a technique called weight box fusion for ensembling to generate final opacity prediction. And using the opacity prediction as we presented, we can generate the non-prediction, and combining with the non-prediction from the expert efficient net model and doing rank average ensembling, we can get the final prediction of none. Here, the reason to use rank average instead of simple algorithmic average is because of the evaluation metric is kind of ranking based, so it's a more reasonable choice. Same thing for the study level labels. We blend the study level labels from efficient data and efficient net and doing rank average to generate the final prediction. So this is our whole pipeline, and here I would like to talk about something that did not work well. The first thing is pseudo labeling on the whole record and BIMCV data. Actually, it works for both the my local cross validation and the public leaderboard, but surprisingly, it failed in private leaderboard. This is not expected. And also, there are some tabular labels or annotations in record and BIMCV data, and we can build some models using those data. I also try to blend the models with my image model predictions, and it worked pretty well for public leaderboard, but it failed in private leaderboard. And compared with these things, the biggest failure of my solution is according to the winning solutions. Comparing with them is I did not do any pre-training using external data like Checkspert. So this is everything I want to present. Thank you.